So what if you could solve a really complicated problem just by asking a bunch of simple yes or no questions? Well, that's the whole idea behind a decision tree, and it's one of the coolest, most intuitive tools in all of machine learning. Today we're going to break down exactly how they work from the ground up.
And to really get it, let's just dive right into a real-world scenario. Imagine you're a bank, okay? You've got this absolute mountain of credit card applications coming in every single day. And for each one, you have to make a call, approve or reject. And believe me, getting it wrong has some serious consequences.
Now, we're not just talking about a little pile of paperwork here. The bank is staring down a massive data problem. And as you're about to see, it's a problem that's spinning out of control.
For starters, the sheer number of applications is just exploding. I mean, a 35% jump? The old way of doing things by hand just can't keep up. It's creating a total bottleneck.
And this is where it gets really scary for the bank. It's not just about being slow. It's about making bad calls. The number of risky approvals, for people who are probably going to default, has almost doubled. That's not just a number on a chart. That is cash walking right out the door. So you look at the data you have, annual incomes, credit scores, you name it, and it's just a mess. It's a jumble of numbers. There's no clear pattern, no obvious rule that tells you what to do. How is any human supposed to make a consistent, smart decision out of all this chaos?
So how do you fix it? Well, this is where our hero of the story steps in, the decision tree. It's this brilliant way of taking all that messy, chaotic data and turning it into a simple, clear roadmap for making decisions.
And what's so cool about this is how simple it starts. The algorithm's first move isn't some crazy complex math. It just looks for the one single question that does the best job of splitting the applicants into more predictable groups. In this case, it's all about income. And just like that, with one question, we've taken a huge step towards bringing some order to this mess.
And then it just does it again. For each of those two new groups, the tree asks another smart, targeted question, this time about credit scores. But notice something really clever here. The rule isn't the same for both groups. The tree is smart enough to know that a good credit score means something different for a high-income person versus a lower-income person. It adapts.
And what we've just built, this simple flowchart of questions, well, that's it. That's a decision tree. That very first question we asked, that's called the root node. Every yes or no path you follow is a branch. And those final endpoints where we land on approved or rejected, those are the leaf nodes. See? Super intuitive.
Okay, but that begs a huge question, right? How in the world did the tree know to ask about income first, and why $110,000? What's the secret sauce here? Well, it all comes down to this kind of quest for purity.
I mean, really think about it. Out of all the possible questions it could have asked, why was income over 110K the absolute best first move? It feels like magic, but it's not. The answer is pure mathematics.
The algorithm has one single mission: to reduce something called impurity. Just think of impurity as a measure of how mixed up a group is, right? A group of applicants that's 50-50 approve and reject is super impure. It's a total toss-up. So the algorithm's job is to search for the one single question that splits that messy group into new subgroups that are as pure or as one-sided as possible.
Let's make this crystal clear. High impurity over on the left, that's a coin toss. You have basically zero confidence about what to do. But low impurity over on the right, now that's a confident prediction. You're pretty darn sure that most people in that group should be approved. Every single split the tree makes is chosen because it gives us the biggest possible drop in impurity, taking us from a state of total confusion to a state of clarity.
So this quest for purity sounds great, right? Like a perfect strategy. But this is where our story takes a little bit of a dark turn, because this obsession with being perfect can lead to a really dangerous trap, a trap called overfitting. See, if you don't stop it, a decision tree will just keep splitting and splitting and splitting until it's created a perfect little rule for every single person in the original data. It becomes this massive, sprawling, super complex tree that hasn't actually learned anything. It has just memorized the past, including all the weird, random flukes and noise.
And that, my friends, is overfitting. It's when your model looks like an absolute genius on the data you trained it on, but the second you show it a brand new application from the real world, it completely falls on its face because it never learned the general rules, just the weird exceptions.
Here's the classic sign. An overfit model looks amazing on the training data, but its performance on new, unseen data is just awful. What we really want is a good fit model, one that's good on the training data, sure, but is also good on new data. That's the proof that it actually learned the real patterns.
So how do we escape this trap? How do we stop the model from trying to be too perfect? Well, we do something that sounds a little counterintuitive. We simplify it. This is the big finale of our story, a technique called pruning. And it's all based on the idea that sometimes less is way, way more.
Pruning is, well, it's exactly what it sounds like. Think of trimming a rose bush to make it healthier. We go back and strategically snip off the branches of the tree that are too specific, the ones that are probably just capturing noise instead of a real, useful pattern. And this isn't just random snipping, it's a really smart process. First, you let the tree grow wild and overfit on purpose. Then, the algorithm goes back and looks at every single branch and calculates a cost for how much complexity it adds. And it asks a simple question. Hey branch, is the tiny bit of accuracy you give me worth the cost of how complicated you make me? If the answer is no, snip, you're gone.
It all boils down to this one simple idea. Pruning stops the tree from just memorizing the noise. It forces it to focus on the big, important patterns, which helps it generalize and handle totally new situations it's never seen before. Because at the end of the day, we don't care how well it did on yesterday's test, we care how well it's going to do on tomorrow's.
So the big takeaway here is pretty profound, isn't it? In machine learning, and maybe in a lot of other things too, the most complicated solution isn't always the best one. A simpler, well-pruned tree that truly understands the fundamentals is way more powerful than a massive, complex one that just memorized a bunch of details. It kind of makes you wonder, right? What decisions in your own life could probably be mapped out with a simple, elegant decision tree?